So to kind of start off, I think we'll just go to the site sort of on the third slide, and then maybe we'll come back to these slides later if we have time. So has everyone signed up for a Kaggle account?
So maybe not everyone. My idea was that just those that have a computer that we'll be using have the Kaggle account, and then the others can sit next to those.
Right. So everyone who has a computer definitely log in. And it's worthwhile to make a Kaggle account because you can look over with your neighbor, but it's really not quite the same as when you do it yourself. And so if you can go to this website, you can go to kaggle.com to register, and then you can go to this link, which is on the third slide, which is the TRABIT 2019 Imaging Biomarkers section.
Shall we maybe ensure that everyone is around the computer device? Are you? I do have the. Okay, good. Is anyone selected? Is anyone not here by someone with a computer? Because then you just move.
I mean.
So maybe do you wanna sit here with Francesco and Anivan?
So if you need to get to the site, go to bit.ly/TRABIT19. Then you'll get to the slides and go to the third slide and you'll have a link.
I think it's okay.
So you don't have to download anything. Nothing, everything runs on the website. You don't have to install anything on your computer. You do it all there, which is part of the reason for using Kaggle is because if you have to install things on your computer, everyone here has different computers. Some people aren't allowed to install anything on their computer. And so it gets incredibly difficult to actually get anything done, particularly in such a short time window. For reference, has anyone used deep learning before? Wow. Okay. That's much higher than I expected. But very few of you have used, or how many have used Python before? Okay, so it's the same number? That was much higher than the checklist looked like, but okay. And Jupyter notebooks? What? Okay, interesting. So that basically what we have here, and who has heard of Kaggle before? And used Kaggle? Like participated in competitions? Really? Okay, wow. Great. So basically the idea of Kaggle is that it's a website that has competitions on it. I don't work for them. I'm not a shareholder or sponsored or anything like that for them. I just find it to be a very useful tool. And so basically when people have problems, and typically this was outside of the medical space, that you have 10,000 customers and you want to know which ones are going to rent movies tomorrow or whatever your problem might be, you give all your data to Kaggle and they make a competition for you so that you can have data scientists all over the world try to solve your problem. And so more recently, they've moved much more into medical imaging, and there's a lot more medical problems of, you have a CT scan, how do you find cancer inside it? And one of the really good things about Kaggle is that, if you're a small group, you only have a limited amount of resources and a limited number of ideas. And so maybe you'll find a good solution to a problem, but chances are you won't. And what Kaggle does is allows you to sort of spread your problem across hundreds of groups all over the world and really have an unbiased, fair way of judging how well everyone deals with these problems. And so it gives you sort of the scope of really, really large teams of data scientists.
And why would people want to solve your problem?
Because you pay them a lot of money.
Oh,
it's a competition, yeah.
Money.
Yeah. Well, money. So this competition doesn't have any prize, unless Mary decides there's some prize that's available for it.
I didn't know about that, so I don't have any.
There's potentially chocolate boxes or something. None. Well, they can have my chocolate box. But maybe. So the prize would be that you have sort of the honor of being the top placed in a very competitive group of summer school students. And so the idea with this is that, yeah, there's competitions, there's public, there's prize money. And the other thing that really drives people is when you're applying for jobs. That you can come to me when you're applying for a job and say, I'm really a phenomenal deep learning expert. I do everything really good. I code all this really great, cool stuff. And how am I supposed to have any idea if you're actually any good at what you say you do? And Kaggle has rankings where you can see how well they did in competitions, where they didn't have access to the answers and they were competing with everyone else. And so if you think you're really good, then you should be able to translate that into performance on Kaggle. Now, there's lots of people on Kaggle who are really good, who aren't necessarily good employees or are difficult to work with or don't really understand business problems or any number of other things that might come up. But the idea is you can at least say, in a fair, unbiased competition, I was able to come up with the best solution. And so it's a really nice way of doing that. And you have the ability to show beyond just I made a bunch of publications or I have a bunch of citations, but that actually I've participated in competitions and done well. And so what this is a little mini competition. And so if we click on data here, we basically have a number of MRI scans of the brain. And the challenge is to predict how old the person in each scan is. And so we have some training data and some testing data, like sort of Jonas mentioned before, that you have sort of these different split into groups. For the training data, we have sort of the scan ID and how old the person is, and then sort of the name of the file. And then for the testing data, we just have the scans. And so your goal is to come up with a model that's able to predict the age from just the image data in the scan. And so this is sort of where the idea of imaging biomarkers or image analysis comes in, is that you need to find some way to analyze these images to figure out the age inside of them. And so to start off, what we'll do is we'll start with this sort of scan overview notebook. So if you go over to kernels, and then click scan overview. Did everyone find that and get that open? And so this is one of the things that's always quite important to do whenever you get a new data set. And so you'll see a notebook like this. And I think you'll have fork kernel. Since I made the notebook, I have slightly different menus than you do. But you should see some button that like edit and make changes, something like that show up for everyone.
Copy and edit.
Exactly, yeah. So that's what fork is. And so you can click fork kernel. Also, all of the kernels that you make are by default private. You have to change them to public if you want other people to see them. And so you'll now get a new kernel that's set up. And so basically this is a Python notebook that's running in the cloud somewhere. So it's not running on your machine, but you're running all of the code through the web browser. And so it's already set up with the data set that we have. So here you see workspace input Trabit 2019. And you can click that to sort of open the folder. And then you can go down to settings and you see that right now it's private. The language is Python. You can also use R, but we're not going to do R at all in this because it's not fantastic for medical imaging. You can turn GPU and internet access on. So if you turn GPU on, that makes a lot more sense for sort of deep learning kernels, but we don't need it right now. And here you can install extra packages if you need certain packages to do certain tasks. And then if you're quite advanced, then there's the ability to use Docker images to really have whatever setup you want in place. But again, we won't do that at all. And so when you start this notebook, you'll see that there's two different kinds of cells. One of them is text cells, so like this top one. And this is using a sort of fairly simple language called Markdown. And so it's like a really simplified version of LaTeX or HTML, where pound sign or hash means this is like a section title. So 1 is a big section, 2 is a medium section, 3 is a small section. And then you just type text normally, and you can have equations in it as well by just using dollar signs. So and you use the same as you would use in LaTeX. So you have the same formulas. Some of the more advanced stuff, I don't know if it works, but for basic formulas, you can have them in there. And the idea for this is that you don't just have your code all by itself in some giant file that no one can understand, but that you can have little notes, and should keep little notes, explaining what you're doing in each step. So you have comments in code, which is already very helpful, but having sort of sections to divide up your code makes it a lot easier for other people to figure out what's going on or to skip to the section that's relevant for them. So right now, we'll sort of use these basic packages. I have sort of descriptions of what most of them are. If you have questions, you can ask about them, but right now we'll just try to skip over that. And what you do is each block, you click this little play arrow next to it to run the code. Is it? I can also drag it over. What do we get?
No. Okay.
How do I get the bottom part? Okay, anyways. So we'll try to focus on the code that's just up here. So the first block, you just click play, and you'll know that it's run by that if you click on the second block, you'll see this in has a 3 next to it, which means 3 blocks have been run so far. Here you see the in is empty, which means this hasn't been run yet. So the next block also does nothing. It just sets up the plots to look nice. Because like MATLAB, Python makes horrible looking plots by default. And so you have to set up the settings so that your plots are readable and usable for other things after, besides just plotting them inside. So the first thing we do here, this is the first real block when you click play on it. And this will load in the training file, where we see the scan ID and the age years, and then the image path. And if that doesn't work, it means you probably didn't run one of the previous 2 blocks before. So did everyone get it open? The text shows up, or? And has everyone used, or who's used pandas before? So less people have used pandas than have done deep learning? Okay. So you can change head. Head just shows you the first 5 lines. You can change it to tail, I think, to show you the last 5 lines, or sample to show you 5 random lines. And this is often very useful because you'll notice many data sets are poorly formatted or have invalid columns inside of them or have, age equals 500. And so just clicking around and sort of sampling different parts of the data will help you see if there's something bizarre you should be paying attention to. The next thing we'll do is this. We can take the column age years, which is the age of the brain, and make a histogram by just using the .hist function in pandas. And so what we'll see is that we really end up with 2 groups of patients. So people that are really young and people that are really old. And of course, this is not a normal data set. This is intentionally picked out so that people are young and old to make it easier to solve the problem. So you don't have a lot of images that looks very similar. You have images of 20-year-old people and images of 90-year-old people. And hopefully their brains look a little bit different, or you can find fairly easy biomarkers for identifying them. And so it's really, there's ones that are under 60 and they're way under 60, and then ones that are over 60 and they're way over 60. So we can then make this thing called age group, where we sort of add a new column and we say if they're over 60, they're old. If they're under 60, they're young. And then use something called value counts, which then show us how many people are in each group. So this is one of the first things that sort of Jonas mentioned was it's quite important to kind of make sure your groups are balanced. And so here you see you have a lot more examples of young people than old people, which means your model could be quite biased if you just train it on this data as they're present there. So it's something you should be aware of, that in this training set, your data are mostly young and very few old, but in reality, your scan distribution might look very different. And so sort of looking at this as a starting point, if this is what you're trying to build a model on top of, clearly if you have a patient that's 50 years old, your model wouldn't necessarily do very well because you're only training it on 20-year-old and 90-year-old patients. And maybe they look like something in between, but maybe they look like something else entirely. And that you have many more young patients than old patients, so it might be kind of hard to generalize what are the differences between young and old. So then here, this is where it starts to get a bit more complicated. So if you understand it, great. If not, it'll probably take a little more sort of review of things to get used to that. And so here we just load the first scan. And so we just take the first row, which is iLock 0, and then load the scan. And so we see here the patient age is 89. The age group is old. The NI path, so the formats, we have images in NIFTY format, which is the more standard medical format to use. And then we have them in HDF5. Who's heard of HDF5 before? Yeah? And have you used it?
Yes.
And why would you use it?
To convert the .dat data to the mat file to process the work in the MATLAB.
Yeah.
So that's why I convert initially to dat to H5.
Yeah.
And then H5 to .mat.
Okay, yeah. So H5, yeah, is a really nice format because it works in MATLAB, it works in R, it works in C++, it works in Java, it works in ImageJ, and it works in Python. And so if you have something in HDF5, you can open it in hopefully pretty much any tool you want. Excel will not open it, but hopefully you're using more advanced tools than that. But that you can basically store your image so that it's easy to open again, and that it handles multiple dimensional data very well. So that, if you have 2D images, JPEG works great, but if you have 3D images, JPEG doesn't work very well. And TIFF works really well with 3D images, but it doesn't work well with 4D or 5D or 6D or 7D. And as you look at MRI sequences or lots of other formats, they often are very, very confusing. And even DICOM formats become very difficult to read in. And so if you put it in HDF5, you can be fairly confident that someone else is able to open it again and figure out what's inside. It's then also quite nice because you can have a lot of different data together. So you can have image data, you can have matrix data, you can have text, so descriptive things, all in the same file, and it's sort of organized clearly. So it's a very popular format for storing data, and if you're looking, you want to collect a lot of data and store it and then give it to other groups. If you do it in HDF5, it'll make your life a little bit easier. So now here, to visualize the data, we use a tool, or we use the library in Python called Matplotlib, which is sort of the easiest standard library to use. And what it tries to do is be as much like MATLAB as possible. So it's not identical, but many of the things have really the same name. And so here we'll show a picture of the scan, and we just take the middle slice. So divided by 2 gets the middle slice there. And now we can see, we're looking at a brain. You're, I assume, much more familiar with these scans than I am. And you can see sort of different structures inside it. It looks fairly normal. Does anything look unusual about this scan? Well, besides the color map. So you can change the color map by just going, comma, CMAP equals gray. Now it looks a little more normal, I guess, for what you're used to seeing.
Can you change
Rotate it.
rotation so that
I would rotate it.
Rotate.
90 degrees on.
yes.
What is the structure for serial to the
No.
The other,
That's
Not like
180.
this.
it's 108. No. Does 90 becomes?
And no functions.
That's quite difficult, huh? Nope.
That's mirror.
Okay.
Does that look normal?
Yeah.
More comfortable with that scan now. Okay, now beyond that, anything of?
The scalp? Scalp?
Yeah.
Not present the scalp.
Yeah. So these images have been pre-processed and the scalp's already been removed. So with most image format, I mean, with DICOM, you often have like a history of all the things that have happened to it. But with other image formats and lots of these competitions in particular, the data have been pre-processed by someone else using different approaches. And so it's quite important for you to actually look at the images carefully and make sure that they've done the same thing to all the images. Because otherwise your model can learn that, images that don't have a scalp are young and images that do have a scalp are old. And clearly that's not what you want your model learning. You want to actually focusing on the image data that's relevant. And so kind of looking at these images, getting a feeling for them, and checking out how different samples look is a quite important task. So it's very boring, it's not super exciting, but if you don't spend time doing that, you'll usually regret it later because you'll find out there's these huge problems. Another thing that's quite useful to do, and I guess this will also annoy you because these are all rotated, I guess, in the wrong way, but you can show the middle slice in each dimension and see, are all the dimensions lined up? Is the resolution in all dimensions similar? And are there kind of artifacts that might show up in just one direction versus the other? You can then go to the sort of most extreme part where you use a function in scikit-image called montage, where it will then take all the slices and make one giant plot out of them. So this is a bit overwhelming to look at. So you can put the brackets in here and go : 2 to skip every other image. And then get a smaller view. We can then add the comma CMAP gray. Oh nope, CMAP goes in the im show, not there, sorry. And then get the grayscale color map. And if you wanted to skip the first 10 images, you could put a 10 before the first colon there, and then a -10 before the last, so that you'd skip the first 10 and the last 10, because those are empty anyways. And then have, actually that's not even enough, so maybe 20. So then you have a much smaller representation where you can now actually go through it and see if there's anything really weird in these images or if bone got left in that wasn't supposed to be left in. So did everyone get that part done? You can then also change the color bar here. So if you go vmin equals 100, or we can vmin equals 0, vmax equals 255. Then you can make it so everything's super, super bright. That's obviously not very helpful. Vmax equals 10,000. Now everything's really dark, and you could go 2,000 to 3,000. I guess that's also not very good. Maybe 1,000 to 2,000. And use it to kind of highlight different structures or different ranges inside of the image. So then this gets, unfortunately, a little bit more complicated again. And this is then how we compare young and old. So I tried to make it as easy as possible, but I appreciate if you haven't used Python, if you haven't used pandas or some of these tools before, this blob of code can be quite confusing. But again, if you just click run, it will work. And it's only if you start changing things that it will sort of screw up. And so what you can try to do on this is get the images rotated so that they look the way they're supposed to look, like we had in this first slice, so that we can compare young and old a little bit better.
How did you flip it again?
So if we go back up here, this is what we had for the first one. guess we can.
Looks different than the original one. That's already a start.
You'll actually find this is how most people learn how to use these tools, that you just find giant other scripts that other people wrote that don't do something correctly, that you then tweak and change parts of it until it works correctly. And by doing that, you learn all the mistakes you can possibly make and hopefully understand better what that code is doing. And so, I mean, one of the things that's a little bit too easy to do with Jupyter or Kaggle kernels is to just click run and run everything and be like, okay, it works perfectly, I'm done. And it's important to kind of go through and try to understand what's actually happening. And there are lots of courses online to do this. You know, you can go to Coursera, probably your universities have courses as well. But ultimately, you'll have to play around with things like this yourself because you know, these libraries are very, very new. And particularly in medical imaging, there's lots of different libraries and there's very few courses covering them. And if there's a course covering it, it probably means the library is out of date. So do you want more time to work on that? Or has everyone gotten the images looking? They're good?
I think they're on like so weird.
Okay. Okay. And so now that you have the images lined up better on your own machine, you can zoom into them a little bit more. You see the fig size here? You can make the fig size much bigger. So if you go to fig size 30 by 20, it'll then make a much higher resolution image that you can really zoom into. And so now, in terms of coming up with imaging biomarkers, what would be sort of the next step you would go? We want to build something that can figure out how old the scan is. We have 2 example scans here. This top one is old, this bottom one is young. I guess we can make it smaller again so that you can actually read that. Seven. Any ideas of how we separate young and old scans? I mean, we could put it in a giant deep learning model and learn magic features and have it spit out the answer for us. But if we were going to start with something simpler, what would you do? What?
Can you get the size of the sponge?
Yeah, and how would we do that? A threshold, yeah? So that would be one thing we could do. So we could try to take a threshold of the image and measure sort of the size of the sort of white material and have that area as a metric that we used. Any other ideas? What? Yeah. So that's actually a lot easier. Potentially the threshold works better. I haven't tried the threshold myself. But so the intensity, if we look at this image, we see that the sort of old scan looks a little bit darker. What that actually means, I have no idea. But we see here, there's a lot more air inside the scan as well. And so if we just look at the average intensity, we'd expect it to be lower for an older scan and higher for a younger scan. And so just to go back to some of the things that Jonas introduced, he talked about this no information. What was the R? Prediction, guess, something like that. The no information thing? Rate.
Yeah.
Yeah. And so what would what would a no information rate for this problem be? Or so what's really fun with scikit or with Python? So he mentioned Weka as like the machine learning tool. So in scikit learn, which is what the machine learning package is in Python, you have something called sort of dummy classifier and dummy regressor. And these are the no information rate tools. And so whenever you build a model, you should always compare it to one of these dummy models, at the very least, to have an idea of how much just kind of almost random guessing would give you. And so for this problem, what would the no information rate be? Or what would we expect?
It's a high intensity than it's young. Otherwise, it's old.
So using intensity is already some information. So no information means you don't even open the image.
Everyone is young.
Everyone is young? Close. So that would be if it were a classification problem. So we're doing a regression problem of actually trying to predict the age. So for a classification problem, the no information rate is just picking the most frequent class. So saying, yep, everyone's young. For a regression problem, what would that be?
The mean age.
Yeah. So if you take the mean age for all the people in your training set, that would be your no information rate. And so what's quite nice with Kaggle as well is that is one of the submissions on the contest. So if you start submitting your results for your predictions for the ages, it will compare it to the no information rate. And you can see if you actually were able to beat that as part of your model. I think in classes that do this, you have that come up quite frequently. So now you can go back to the original page, and you have a second notebook here called MRI age using brightness. And then you see this number next to the model, and what that number is the score that model got, or that kernel got, when it was submitted to the competition. And so what's very nice about this is if you go to other Kaggle competitions, there should be a bunch of them going on right now. So I think there's one from Sim. Here it is. So it's a pneumothorax segmentation challenge. Let me just get to here. We can go to the kernels. And so you can see lots of kernels here, train your own data. But this is then the ones that are very interesting because you can actually see that got a 0.64 score in the competition. And so then you can go to the leaderboard and see that 0.78 is one of the benchmarks. I guess there's lots of submissions already for this. What is this number? I guess this is the overlap accuracy or one of these metrics. So there's lots of people that got that score, and that you can then see where people placed and where different models landed on this result list. And so here you can see the code to get that one. So a lot of these people didn't submit code with their models, which means you can't see it. But here you can click and see what they actually submitted and what the result was. And so it's quite helpful for going through these data sets that you can actually get a feeling for not only what are what's the range in the competition, but what people were doing to get different results. And so obviously, if you're sharing your code with everyone, you're probably not trying to win, but it can be very useful for learning. And as a lot of the people on here are students, having your code shared, having other people comment on it, have people change it and make revisions, help everyone do better. So if you're a bit more altruistic, you can share your code or at least try new ideas. And if you talk to the people who are really, really experts at these competitions, they often form teams with other people. And so if you have a really good result here, they might form a team with you, and then you can share the prize money if your model ends up winning. But anyways, for this one, 9.5, what that means for us is that's the mean absolute error. And so what does that 9.5 mean?
It's a mean error between what you predicted and the real age of the people.
Yeah. And so it's the years off you were. And so 9.5 means you were plus or minus 9 years on average from what the actual age of the person was. And so it's not fantastic, but it's not terrible. It's better than sort of random guessing. So you can now go into this notebook and click the same thing we did before, where you fork kernel. And so you can quickly go through the first blocks again. Oh, just click. Play, play. And so everything's the same as it was in the first notebook. Make sure you don't accidentally highlight something when you click play. You can also do Shift-Enter to make it go a little bit quicker, because clicking the play button can be kind of annoying. And so what we have here is we make this calc brightness function. So this is the biomarker that we have. And so what it does is it takes in the image data and it takes the average of it. So NP is a package in Python called NumPy that does all the sort of array, linear algebra, matrix processing. And so we use one of the simplest functions in there, which just takes the average of all of the image data. And so we can do Shift-Enter there, and we see that the average is 232.85. So for one image, that doesn't really mean anything. Since it's MRI, the units aren't really that quantitative anyways. But we can now apply it to all scans. And so here, we can run this block. This will take a little while because it has to load in all the images. And then spit out sort of what the brightness was for each one. So we can use a plotting library in Python called Seaborn, which we've imported as SNS. And then we can run that and we can see the age in years on the y-axis and the brightness on the, the age in years on the x-axis, the brightness on the y-axis. And we use the function lmplot, which then automatically fits a linear model for us. And so it's just sort of a nice handy tool that if you think there might be a linear correlation in what you're doing, you can plot it out. And we see that actually a linear relationship was not a terrible guess for what we're doing, and that there's clearly a difference between sort of the younger and the older. You know, there's lots of outliers, but it's not an awful starting point. Here we take a model from scikit-learn. This is just basic linear regression, so there's nothing fancy in this at all. And it does least squares linear regression. When we click play, it then runs all of these lines. This fits the model, and then that shows us the slope. So since there's only one input, which is the brightness, the slope just corresponds to what does increased brightness mean for the age prediction. And so as you get a higher brightness, your age goes down. That's right. So that doesn't mean 9 brightness points per year. That means 9 years per brightness point. So that's always sort of important to think about. And again, using really simple models like linear regression might seem really pointless because, you know, it's not going to be complicated enough to solve your problem, but they're simple enough that you can actually understand what they're doing. So you can go through here and say, there's only one coefficient. What does this 9 actually mean? And does this correspond with what my intuition would tell me about the problem? And if this were, you know, plus 20, that would not correspond to what we'd expect. And so maybe there's noise in our data. Maybe we've mixed the labels up or loaded the wrong images or loaded the same image for everything. And so it's very helpful to actually go through and try to understand what's inside this. So we can now apply it to the test data. And here it's fairly quick because there's many fewer test samples. And then run this prediction. And we see that it works perfectly, which is what we'd expect. So if you plot the predicted age in years versus the brightness, in the test data you get a perfect line. But we don't know what the actual age in years is. This is just showing what the output of our model was. And so now here we can save the output where we have scan ID and age in years as the only two columns in our output. And so one of the things Kaggle is quite strict about is that all the submissions for your results have to be formatted in just that format. And so usually just two columns. You want to make sure index is turned off, and then you can submit it. And so once you've done that, you can click the commit button, and it will run your model from start to finish. And that you can click here to open the result. And so here it's still running. And then you can click on it and see that it takes a little while. I mean, it should only take 30 seconds to run the whole thing, but still. Click refresh. And then you should be able to go down to output. So here we see all the different sections from the text boxes that we had. So each one of those hash marks becomes a section, which makes it a lot easier to go through. And now we can click output and then submit to competition. And that once you do that, you should start showing up on the results board. So everyone should have pretty much the same result. I mean, everyone ran exactly the same code. And hopefully everyone beat, you can try. Beat the benchmarks. Why do the benchmarks not show up? Host. Now we have the benchmarks showing up. Okay, so now we see the sort of the no information guess would have been 21.6. The linear brightness is 9.51063. And that everyone who submitted it has gotten exactly the same result. So can anyone think of how you'd make this current model better? Any ideas? So we have the threshold, which would be sort of a different approach that we could try.
You could try to segment the different tissues and more in details, for example, the size of the ventricles compared to the total size.
Yeah, but that would be quite complicated to do, right? I mean, I don't know how to segment that. Maybe you could manually segment them in all the images, but we have 100 images, and I think we don't have too much more time left for this block. So that could be quite tricky to get done. So of course, there's lots of things you could do to make your results a lot more complicated. You could fit an atlas to it, maybe use the atlas sizes as a basis. In terms of the simple data that we've input, any ideas for what we could do to make that better? Change the what? Yeah? Okay. What model would you try? Is there maybe something between?
Any other shallow classifier?
Yeah? What would you use? SVM?
SVN is quite sophisticated and something more simple.
Yeah? I mean, we could try SVM. So there's a few things we can do at this point. So we have the scan overview. We can close. We have this. So now we've done this with age and a linear regression. So we could try doing one with thresholding. We could try doing one with SVM or another simple classifier. Or we could try sort of balancing the data better. Does anyone have any preference on what would be most interesting to see or most interesting? Well, so right now we have a huge gap between young and old. And we train the model with the same number of examples from both. And so it fits a line that works much better for the young than it does for the old.
And then you would just kick out some young, or would you do the balance?
Well, so that was what Jonas talked about in a much more detail than we have time for. But the easiest things to do is kick out the young. Potentially the more sensible thing to do is to oversample the old, which means you resample a lot of the ones in the old group. So if we wanted to do that, we can actually do that fairly easily. So we have the brightness here. We've calculated the brightness. And what we can do is we can just make a new, so you can click the code block above there and go balanced train DF. Group by. Live coding is not ever that easy, but hopefully I'll get it correct. 60. Apply. So right now we have 70 samples in total. And so what we could do is maybe sample 50 from each group. So I apologize because this is going to be quite tricky to read. Oop. I'll drop it's true. So we saw the first issue you run into here. So basically what this does is it says for train DF, we group it by age above or below 60 years. So this is 1 if it's above 60 years, it's 0 if it's below. And then what we say is we want to take each group and sample 50 random people from it. And so that's what the .sample command does. We end up with the error message because there aren't 50 people to sample from each group. And so you have to add the argument replace equals true, which means you can sample the same person more than once, or the same scan more than once. You then have the reset index to sort of clean it all up at the end. So now we can resample it, and we see from these peaks, there's 50 in this group, and there's probably 50 in this older group as well. And so now we can run it on train DF, and we see that we have this line, and we can run it on balanced train DF, and that we see we get a slightly different line. We can now change the train DF here to balanced. And then see that we get now 9.7 instead of 9.0. And so this coefficient is now less biased by the younger age people and includes sort of equally from both groups. And so now the model's trained. We don't need to balance the test set because the test set, we just apply the model to, it doesn't change. And that we can now click commit and run the model. And so if we go to the output from it, we should be able to see when it's finished. Is it not? And to be more patient. Okay, now it's finished. And that we can go to output and then submit to competition. And what do we see? No, the results here.
Worse.
Yeah, so higher error. So what does that mean? Or why do we think that happens?
But isn't that cheating and not bit to do the oversampling of the big video?
It's not cheating.
I mean, not cheating.
It's not necessarily the most statistically sound thing you can do. There are lots more advanced techniques for like picking the samples well or trying to divide into groups that make more sense.
Because we just duplicated some
Yeah.
randomly picked old people, right?
Right. So we haven't actually made more data for our model to train with. We've just taken the data and sampled it so that they were in even groups. But the fact that the model does worse, does anyone have like an explanation for why that might be?
Overfit.
Overfit could be it. Usually with linear regression, with only one parameter, it's fairly safe that you're not overfitting too much. It's one of the nice things about it because there's two things it learns, the coefficient and the offset. And so it's, yeah, can be overfit, of course, in certain situations, but most of the time you're fairly safe. Or what does it tell us about the balance of the data in the test set?
Maybe it's as balanced, as unbalanced as in the training set.
Yeah, that's what we see. Or that would be a very good explanation for why that gets worse. And so by balancing out the training set, we actually make it less likely to work well on the test set. And given the fact that this is a competition, it's very likely that I just took all the data sets and kind of randomly split them into training and test. And so you'd expect the balance to be very similar in both. In real world situations, of course, it can be very different. But in this situation, it's not. So if we go back, I guess we should try to have a short break at some point.
Up to them. Do you want to have a short break or do you want to continue? Oh,
I guess we can continue. Or do you want a short break now? Sure, we can take a break.